All right, well, attendance is a little sparse today, but that's okay. It's midterm week. And in accordance with that, I did have somebody ask a question about, is any of this stuff gonna be on the midterm? To which I say, no, none of this is gonna be on the midterm because we don't have a midterm in this class. So it will all be on the final though. You're not getting away with it for long, but you don't have to worry about it for another couple weeks. Along those same lines, Monday's lab already heard this, but our next in-class quiz is next Wednesday. So because it's midterm week, because we don't have class on Monday, I'm gonna say we're not gonna have a weekend quiz this week. Study for your polyatomic ions quiz, study for your other midterms, get some rest, and come in on Wednesday ready for the polyatomic ions quiz, right? I'm gonna talk about the rest of these as I try and test myself and see how many of your names I have down at this point. It's not all of you yet, I'm sorry to say, but there's a lot of you in this class. So I'm still gonna have to guess on some of your names. Somebody asked, why does the ice cube melt faster with a cold surface rather than a hot surface? I don't think that that's a thing. I'm pretty sure that this student mixed up a different weird fact, which is that ice freezes faster if you start with hot water. If you start with hot water and put it into an ice cube tray and put it into the freezer, it will freeze faster. And you can demonstrate this, and it's not fully understood, so it's still not a perfect to explain, but it's basically the thought is because warm water circulates better, you get more uniform temperature inside because the warm water is circulating more, which helps it freeze fast all the way through faster. You won't get like if you just think about getting like a what's the word I'm looking for? A layer of ice on top. That will happen faster with cold water, but if you're talking about freezing an ice cube solid all the way through, that happens faster with hot water, which is interesting. A couple of people asked about iron and rust. Basically, turns out chemical reactions, most chemical reactions just involve moving electrons around. If you move electrons around, then you get more stable situations. Basically, you go from something, this actually is relevant to our class. Because for instance, if you start with iron as a solid and you let it react with oxygen as a gas, oxygen has 6 valence electrons normally, right? It's a non-metal, and when you put the non-metals together, they naturally make covalent bonds with each other, so you don't actually have oxygen atoms. You have oxygen molecules like O2. But what happens is those oxygens are trying to grab electrons and fill their valences, right? They kind of have them full. And when you're making this covalent compound, but they're not as stable as they could be. This is a concept we're going to talk about a lot today. We're going to talk about the idea of electronegativity, which is basically how tightly do different elements pull electrons towards themselves. Oxygen is very electronegative, which means it's really good at pulling electrons towards itself. So forcing an electron or an oxygen to share electrons with another oxygen is not super stable. So what happens instead is oxygen grabs electrons from the iron, because the iron's a metal, it's trying to give away electrons. So you wind up making iron 3 oxide as a result, and everything is more stable that way because the iron lost its electrons that it had in its valence. So the iron's able to only have full valences now, and each of the oxygens gets to fill its valence as well by pulling electrons towards itself. So that's how rust happens. If you don't have oxygen around, iron doesn't rust. It happens even faster if in certain conditions, like if it's high humidity, if there's salt water in the air, because that basically speeds this process up. But if you just leave iron exposed to oxygen, it will always form this given enough time. In fact, that's what gives Mars its red color. Is Mars, instead of having Earth is made predominantly of silicon and oxygen in the crust, Mars is made predominantly of iron and oxygen in the crust. So it's red because it's rust colored. If we want this to go backwards, we basically just need to force electrons to go the other way. It happens this way naturally because that's what gives the electrons the oxygen. If you supply it with high energy electrons by, say, attaching it to a voltage source, we can force the electrons to go back the other way. Right, so if you think about energy as being altitude, as being height, here we started at a high energy state and then naturally we wound up down here. Attaching this to a voltage source is sort of like if you picture picking up one corner of a tarp and lifting it up, and then all the electrons go back the other way. So we can get things to move backwards if we change the conditions. More on that, and lots more on that when we get to Gen Chem, but when we talk more about reactions in general. Somebody asked, is there anything smaller than an electron? And to that I say, I'm not a theoretical physicist. If you want a good place to start, the Wikipedia page that you should start from is called the Standard Model. You just look up the Standard Model. That's the current understanding of how forces and particles in our universe work. I believe electrons are what they call a fundamental particle, meaning that you can't break down an electron into anything smaller. That doesn't mean there's not smaller things out there, just that an electron is not made of smaller things. Are we going to talk about biology? Sure. Yeah, no, we'll talk about biology, especially when we get into talking about reactions more. Somebody else asked about how does digestion of sugars and things like that work. When we get into reactions and energy, we'll spend a fair bit of time using biological examples because I know most of people in here, well, everybody in here is a biological organism that has some interest in how biology works, even if it's not your chosen field of study. So we use a lot of biology examples once we get there. Last two, is it true atoms split when they explode? If so, can you explain why and how? Yes, I can. In fact, if we had an extra 2 weeks tied onto this course, we'd actually cover nuclear chemistry in more detail. But for now, just the brief overview is basically if you look at something like, say, fluorine, look at the fluorine only has one isotope on Earth. So the mass of fluorine 19 is 18.998 AMU. So fluorine's is number 9 on the periodic table. So that means it's 9 protons and 10 neutrons. Where this gets weird is that a proton has a mass of 1.007. 1.0078 AMU. And neutrons have a mass of 1.0087 AMU. Which means if you took 9 protons and 10 neutrons, should it be more than 19 or less than 19? If you just added the pieces up. More than 19. All of our pieces have a mass greater than 1, and we're adding 19 of them together. It should be a mass more than 19. But that's not what the mass of fluorine actually is. that difference in mass between what the pieces should add up to and what the nucleus actually does add up to is what led Einstein to his most famous equation, which is Einstein with this equation demonstrated that mass is just another form of energy, basically. The missing mass between the parts and the total goes into holding that nucleus together. It's called the nuclear binding energy. If you took this nucleus and you split it up into all its individual pieces, that energy all gets released at once. Which is, and it turns out to be a ton of energy, because even though it's a small difference in mass, C is 3.00 times 10 to the 8 meters per second, right? Remember that from our light lab last week? You square that, you get 9 times 10 to the 16. Even though it's a really small difference in mass, C squared is really, really big number. So basically that's what the phrase means, splitting the atom, is basically if you do this with larger nuclei, like uranium, when you split it up into pieces, you get smaller pieces. You don't split up all of the parts, but you get a couple smaller nuclei and some neutrons along with it. And those have less nuclear binding energy. And so that releases all the extra mass gets released as energy according to this equation. So yes, if you split an atom, the pieces, if it's a big nucleus, the pieces that you come away with are usually going to have extra energy that gets given to the surroundings, which if you get enough of those atoms in the same place at the same time, looks like an explosion. So that's all a nuclear bomb is really, is basically taking all these naturally occurring nuclear or radioactive isotopes and gathering them all into one place so that a whole bunch of those nuclear reactions happen all at once. So then the Manhattan Project was more of an engineering project than it was a science project, because they already knew that this would happen. The question was, how big can we get these chunks of uranium without it spontaneously going through a meltdown and blowing us up? How do we control when it detonates? Was more what the Manhattan Project was about. How do we make uranium, and how do we control when it detonates? Non-trivial issues, don't get me wrong, but it actually is more engineering than science, even though they had all these really smart scientists working on it. And just because I can't resist a question about organic chemistry, nitrogen contains amine that can have a fishy smell. That's actually a little bit backwards. Amines are an organic compound that have nitrogen in them. So if you've heard of amino acids that our proteins are built out of, amines are what happen if you let an amino acid, if you let proteins get broken down by microbes or just exposed to air over time, you wind up with that acid part of the amino acids winds up leaving, and you just get amines left over. And so amines smell, they don't just smell fishy, they smell like rotting meat. Depending on the exact type of amine, it can smell like rotting fish or rotting meat. Some of them can even smell a little bit like dirt, but not like in a pleasant way. And it's basically, it sounds really terrible smelling. They are really terrible smelling. And that's actually really interesting, because the only reason they smell terrible to us is because it's a biologically evolved mechanism that tells us, hey, that dead fish on the beach over there, you probably shouldn't eat it or you're going to get sick. It's basically, it's the same way that, so I change a lot of diapers, or I'm on my way out of changing diapers soon. We all have an inborn biological drive to avoid poop, because that's how diseases get passed on and parasites get passed on. So it's an evolved instinct to avoid things that smell like poop, or to avoid things that smell like dead fish. There's a reason it smells so bad, and it's because it helped keep us alive. as a species earlier on in our evolutionary history. So despite that seeming like a very simple question, there's a lot to it. I liked that question. All right, I'm going to continue handing back quizzes while you all try and draw Lewis dot structures. Reminder, steps for drawing a Lewis dot structure. Count valence electrons. Pick the central atom. If there's only two atoms, do you have a central atom? No. No, so you just put them next to each other. You can't have the middle if there's only 2 points, right? Fill all valences. So give these a try. And then we'll work through them together. Luciana? What's name? Sorry.
Siani.
Oh, Siani. Okay. There you go. Rena. Pardon me, the ribbons here. Maybe it's process of elimination. Almost, right? Oh, yeah. Oh, yeah.
Yeah.
Bias. Dubious. All right, a quick note about these as I'm handing them back. For the most part, everybody did just fine. If your score wasn't what you hoped it would be, then on the next in-class quiz, flashcards. Flashcards are, you can't go wrong with flashcards when it comes to memorizing short things like this. Just put the time in this weekend and you should be okay. The one thing almost everybody did that I didn't take off points for this time, but moving forward I will. You got to make it clear that that's an L on chlorine. Right? And just write it like that. That could be CI or it could be CL. I don't know what that is. So either put a tail on it, write it in cursive, something, so that you can indicate that that's not an I, that that's distinctly an L. I mean, it's never going to be a huge deduction unless it happens to be one of the cases where it actually does cause you to get the wrong like molecular weight or something like that. But for the most part, we just want to be really, really careful with capitalization. The other one that I did see a few of you wrote sodium as Na. Don't capitalize the second letter. Never capitalize the second letter. You have to adjust the way you write things. When you're writing atomic symbols, that's not the end of the world. You just need to be really careful that you're not writing that. Because that molecule is very different than that molecule. Sodium sulfide is not the same thing as nitrogen arsenide. So we need to be careful with our capitalization when it comes to these atomic symbols, just like with units, right? Beyond that though, it's easy to miss a few of these. It's not the end of the world. I didn't necessarily expect very many 10s. I was hoping for more 9 somethings, but it's the class average is about where it usually is when I get this case. So y'all are doing just fine. You individually want to do better, study more. I'll help you with it. All right, let's work on these atomic symbols. Or not atomic symbols. I'm erasing atomic symbols. Lewis dot structures. How many valence electrons does chlorine have? Each chlorine has 7 and there's 2 of them. So 14 electrons total. Write a chlorine next to another chlorine. If we know that there's 2 atoms and they're part of the same molecule, we know they have to be connected, right? So we can start by drawing a bond between them. How many electrons did that use? 2. 12 electrons left. How many does the left-hand chlorine still need? 6. Needs 3 pairs, so a total of 6 more electrons, right? Six electrons left. How many does the right-hand chlorine still need? Also 6. When it's a nice symmetrical molecule, that kind of helps things sometimes, right? Did we use the right number of electrons? Yes. Does everything have a full valence? Yes. That's our Lewis dot structure for chlorine. All right. How about oxygen? O2 has, each oxygen has 6 electrons, and there's 2 of them, gives us a total of 12. Put our two oxygens next to each other. Might as well connect them while we're at it. How many electrons did I use? 2. I'm going to keep harping on that because it's really easy to forget that there's 2 electrons in every bond. I'm going to keep asking you that even when it's the same answer every time until nobody could possibly mix up how many electrons are in a bond. How many electrons are on the left-hand oxygen, or does it still need? How many electrons, as it's drawn right now, how many more electrons do we need to give this oxygen? 6 more. 1, 2, 3, 4, 5, 6. 4 electrons left. The oxygen on the right also needs 6 electrons. We don't have 6 electrons anymore, right? Might as well use up the 4 electrons we have. 0 electrons left. So we use the right number of electrons. Is everything stable? No, we still have an incomplete valence shell on the right-hand oxygen. So if we run out of electrons and we still have a vacant spot, what do? We're going to make a double bond. So the trick with the double bonds is you can't forget to erase a pair from the oxygen that you're going to make share more. We have to erase 2 of them and turn them into a bond. And so my recommendation, you can do what works for you. My recommendation is don't draw the double bond until after you erase the first set. Right, because otherwise it's way too easy to draw the double bond and then forget to go back and erase the other ones. And if we had it drawn like this, that's wrong for 2 reasons. Most importantly, that's more than 12 electrons. We can't make electrons out of nothing. Secondly, we gave this oxygen 10 valence electrons. Oxygens can't have 10 valence electrons. Nothing in the second row of the periodic table can have more than 8 valence electrons. We're trying to get to 8 electrons and no more. So to avoid doing that, you erase them before you draw it. Even if I'm not going to forget, it makes me uncomfortable to have it drawn that way. So I don't want to draw an oxygen temporarily with 10 valence electrons. What's nitrogen going to look like? 5 valence electrons times 2. 10 electrons total. Valence electrons total. How many electrons did I just use? 2. Since we can't start at the outside and work our way in, we'll just pick one side or the other. I think left to right, so we'll go with the left-hand one. We're going to use 6 electrons to finish filling up that nitrogen's valence. There's only 2 electrons left. So where do they go? On the other side. So now we're going to start. We've run out of electrons. We still haven't finished filling the right-hand nitrogen's valence shell. So we're going to start making double bonds. Erase. Draw another bond. We good? The right-hand nitrogen still only has 6 valence electrons, and we need to get to 8. So we just do it again. Erase another lone pair and make another extra bond. Did we use the right number of electrons? There's 10 electrons there, just like we counted at the beginning. Does everything have a full valence? Yes. Yes. Good to go. All right, this brings up an interesting feature of the nonmetals. The nonmetals, if you put the nonmetals with each other in their pure elemental form, like nitrogen, if you just had nitrogen as an atom, its fluid style structure on its own would look something like this. Not very stable, right? But if you have a bunch of these sitting next to each other, they'll naturally form into these molecules, because this way everything can have a full valence. Even though it's still neutral, it's still just pure nitrogen, it'll naturally form these diatomic molecules. Di means 2, right? So diatomic just means you're making molecule out of 2 atoms. There's a list of diatomic elements that when they're in their pure neutral state, when they're in their elemental state, they naturally form diatomic molecules. And if nitrogen is one of them, can anybody give me another one? Oxygen. Chlorine. Chlorine, since it was on the previous page. With sulfur. Carbon does not become a diatom or a diatomic molecule because you can't make a quadruple bond. Carbon would need a quadruple bond, so carbon forms either graphite or diamond instead when it's in its pure elemental state. So it still makes bonds with the other carbons next to it to become more stable. So it's similar logic, but it doesn't turn into a gas. So if chlorine does it, what else is going to have similar properties to chlorine? Bromine. Say that again, Jake.
All the gases with a negative charge.
All those gases that'll make a negative charge. So if you look at your periodic table, there's a whole bunch of them on column 17 that are naturally gases. Anything that's naturally a gas, but it's not a noble gas, is going to do something like this. So chlorine, bromine, fluorine, iodine actually forms a solid at room temperature, and bromine's a liquid at room temperature, but they both do the same thing. They're just big enough that they still stick together at room temperature, but they still do the same thing. And the other one that you could sometimes put into column 17, when we started talking about electron configuration in orbitals, do you remember what element I said you could draw in column 17? What else needs 1 electron to become stable?
Hydrogen.
Hydrogen. Hydrogen needs 1 electron to be stable, so hydrogen will also do the same thing. The other nonmetals, they have, like I said with carbon, they have other sort of structures that they form to make themselves more stable. Like phosphorus has a couple different crystal structures, but they're not gases and they're more complicated. Like sulfur exists when it's pure sulfur as either S8 or S12, depending on the conditions. I'm not going to ask you to memorize that. That's less relevant. Usually, if we have pure sulfur, we'll just write sulfur solid. Same with carbon. Unless the specific type matters, then we'll just write it like that. The other one that you see is phosphorus. You've heard of white phosphorus versus red phosphorus versus purple phosphorus. Those are all pure phosphorus. But depending on the conditions, they kind of arrange themselves in a little bit different shapes. So again, I'm not going to ask you to memorize that. That's more of a material science thing. Because it has to do with the fact that they're solid at room temperature and they make more than one bond. Iodine's solid at room temperature, but it still only wants to make one bond. It only has one vacancy, so it still makes this diatomic molecule. So if I asked you to name these compounds, if I said, what is the name of that? Dioxide, dioxygen. If you have pure oxygen, it automatically arranges itself this way. So we actually just call it oxygen. Or elemental oxygen. So if you just say oxygen or just say nitrogen, you mean these versions of it. You actually specify, if we actually had some really unstable state where we actually had like chlorine in its atomic state with 7 valence electrons in not forming a Cl2 molecule, we would actually specify that's atomic chlorine. If we just say chlorine, it means Cl2. We just say bromine, it means Br2. If we say atomic bromine, that would mean a single atom. And because that's the exception, this is the normal case under normal conditions, this is what we see. When I say normal conditions, I mean like anything short of in the center of a sun. If you get to make these into a plasma, then that's a different thing that's happening. And you get a whole different system, but those don't occur naturally on Earth. What about this last one? CH2O. We haven't done one with 3 different atoms yet, have we? Did it change any of our normal steps? There's no reason it should. We draw in the Lewis dot structure, we're still counting valence electrons and we're trying to arrange everything to fill all the valences, right? So 1 carbon has 4 valence electrons plus 2 hydrogens. Each hydrogen has how many? 1 electron plus an oxygen, which has 6 valence electrons. So that gives us a total of 12, right? What's going to go in the middle? Why carbon?
As that's the most available electron.
It has the most vacancies. Bianca, why oxygen? I'm not saying it's wrong or right. I'm just asking what your logic was. The higher number. So, right line of thinking, but the wrong direction. Oxygen has more valence electrons, which means it's less likely to be in the middle. Because we want to put whatever has the most vacancies goes in the middle. And I'll give you a better way of describing that when we talk about electronegativity in more details later. So we're gonna put carbon in the middle. Just start by putting everything else around it. And then we know if they're all attached to the carbon, we've got to draw 3 bonds at least, right? How many electrons did I use? 6. 6 electrons left. Where should I put them?
Double bond everywhere.
That would use another 6 if we did that. That doesn't look right though. Why doesn't that look right? What about the hydrogens? Hydrogens only want to gain 1 electron. Hydrogens can only have 2 valence electrons at most. So when in doubt, start at the outside and make everything satisfied and work your way in. Are the hydrogens satisfied? They only want 2 electrons in their valence. They're good. How many does the oxygen still need?
6.
We need to get to a total of 8 still. It only has 2. We're gonna give it 6 more. Conveniently, that uses up all of our electrons, right? No electrons left. But the carbon. What about the carbon, Bianca? It's not happy yet. It needs what?
It's 2 more.
2 more electrons. So if we run out of electrons and we still need more on the carbon, we're going to make a double bond. Erase a pair. Turn it into a double bond. Did we use the right number of electrons? Yep. 12 electrons there total. 2, 4, 6, 8, 10, 12. And everything has full valence. Right? The oxygen's got 8 electrons, the carbon's got 8 electrons, each hydrogen has 2 electrons. Good to go. Does anybody know what this molecule is? Historically, if you're in A&P, you would have smelled it last week when you did your dissections. Formaldehyde.
Wait,
It's not, they don't use formaldehyde anymore, I don't think, in the preserved pigs that you all cut open, you monsters. Sorry, dissections are not my favorite thing in the world.
It's like it names formaldehyde.
The old school root name, 4 means 1. And that actually comes from the Latin, not for the word one, but from the Latin for the word ant, interestingly enough. The Latin word, maybe it's Greek, I think Latin word for ant is formica. And the first time they found some of these small organic molecules, one of the first molecules they found was formic acid, which they actually got because that's actually what inside an ant's carapace. Like instead of blood, ants have formic acid inside of them. So if you've ever had like ants in your kitchen, if you squish a whole bunch of them at once, there's that really kind of like weird sweet smell that you get, that's formic acid. And so they named formic acid after the ants. And then they realized that there's a bunch of other organic compounds that also only have 1 carbon in them. So formaldehyde comes from formic acid, which comes from formica. That's not the common name. Now, if we were naming this using the modern naming conventions, we'd name it methanaldehyde. Because meth means 1 in organic chemistry. All right. So Lewis dot structures. They're tricky. Feels like you're making stuff up and when you have a blank piece of paper in front of you, right? That's a normal feeling. Remember our steps, remember our goals with these Lewis dot structures is use the right number of electrons, fill all the valences. Right? And the more we practice that, the more it's going to feel second nature, at least less unnatural. Questions on Lewis dot structures?
What's the theory behind not being able to make a quadruple bond?
So basically, you need space between the 2 atoms to be able to do that. And turns out these different orbital shapes that we got, remember p orbital versus the s orbital had different shapes. When you mix them together, it turns out those are just different functions that describe the shape in 3 dimensions where you're likely to find an electron. You can actually get, if you're trying to make bonds between different atoms, you can get lower energies if you mix those different orbital shapes together. In a way, it's called hybridization. It's basically, like making, if you've taken a math class where you had something that looked like, let's say you've got f of x equals 2x and g of x is 12 and h of x is equal to f of x plus g of x. Remember doing something similar to that where you added functions together? Basically, when we mix these different orbital functions together, we make a weighted average of them. And that gives us a different orbital shape that actually looks like the orbitals overlapping on top of each other. So we can actually say what the shape of the bonds looks like by mixing together the different atomic orbital functions. And that limits us to where we can put them. A single bond, so let's look, if we looked at N2, the first bond that we made between the two nitrogens basically looks like two balloons overlapping with each other. And if you picture like shading in where they're overlapping with each other, a strong bond means that your orbitals are able to overlap with each other a lot. When we add another bond on that to make it a double bond, it looks kind of like this sort of above and below, where one side of this is shaded to have a certain phase. You basically need them to be above and below.
There's no.
So that, because it can't overlap with the blue one, with the single bond. If we make it a triple bond, how do we find room for a triple bond? How? Yeah, in and out. It's three-dimensional, right? That's exactly right. So when we make it a triple bond, we get something that looks like this, and then behind it, on the other side, we get something that looks like that. Where would we even put a quadruple bond? There's like not a whole lot of space left. In theory, you can make a quadruple bond as if you involve the d orbitals, because the shape of the d orbitals kind of fits in between these. And they can look more like a clover leaf than just a figure 8. But carbon doesn't have a d orbital.
But with later atoms, are you able?
Later atoms, in theory, I think the paper that I read that said that they made a compound that had a quadruple bond in it was using manganese. So it's in theory doable, but it's exceptionally unstable, because as soon as you let oxygen in, it basically is going to break those up and form manganese oxide instead. So good question. Obviously I like to talk about that because that's what my research in grad school was on, molecular orbitals and how they overlap in organic compounds. So you asked the right question to get me off on a tangent there. But that's beyond we tackle that in more depth when we get to Gen Chem, and then we keep using those ideas in organic.
Thank you.
All right. So before we take a break, I want to introduce another topic. It's an extension of this idea of Lewis dot structures. The reason we draw Lewis dot structures is, one, because it can show us if a molecule is stable or not. If you can make a stable Lewis dot structure that meets our criteria, odds are that's a molecule that's stable enough it can exist. But it also is sort of a stepping stone that's going to allow us to describe not just where the electrons are, but also what is the shape of a molecule. Right? And so we can know something about the shape of a molecule if we know the Lewis dot structure, and if we remember a couple key ideas. Number one, pretty much all of the volume of these atoms and molecules is electrons. Electrons are tiny in terms of mass, but they take up almost all of the space. The nucleus is a tiny little pinprick right in the middle of all these orbitals, right? So if almost all of the atomic volume is electrons, and electrons are negatively charged, what do electrons do to other electrons? They're going to repel each other, right? Similar charges push each other away. So if similar charges repel, think I have, Feynman diagram. So this is called a Feynman diagram. I'm not gonna have you draw these, but this is more, Feynman was one of those scientists that worked on the Manhattan Project. He was one of the junior scientists at the time because he was only like 22 during World War II. But he won a Nobel Prize after World War II for basically finding a way to describe using diagrams how different molecules, different particles interact with each other. So this Feynman diagram right here was the basis of a Nobel Prize in physics. He just said, well, it's really hard to describe this, so I'm just going to draw a picture. He said, what this is showing is that when two electrons come towards each other, there's this little interaction that he labeled with the Greek letter gamma that pushes each other away. And so the force between these electrons is based on how close they are to each other. So there's a lot of math behind this picture. But all this is saying is that electrons push away other electrons. So if we have two different clouds of electrons around a central atom, they're going to naturally arrange themselves so that they're pushing each other away. So they're as far away from each other as they can be. So, but we don't talk about distances in terms of, well, distance when we're talking about atoms, because these two clouds of electrons still have to be in the same valence shell around this atom, right? So they still have to be, they can't really get that far away in terms of a distance, but they can arrange themselves to be as opposite as possible while still being around this central atom. So we talk about it in terms of degrees. The furthest apart you can get two clouds of electrons is 180 degrees from each other. Makes sense, right? We're not going to put a number like picometers or something to it. We can just say, if you have two groups of electrons around an atom, they're going to naturally be pointed 180 degrees from each other. Just because electrons are negatively charged and negatives push away other negatives. What would it look like if there were three clouds of electrons?
So,
And we could draw it like I did for the formaldehyde. Is that evenly spaced though? This will naturally rearrange itself so that everything is close to evenly spaced. So get everything as far apart from each other as possible. So if we have 360 degrees to work with, what's the furthest apart you can get three things? The other molecule we use all the time as an example for this one is BF3, because it's Lewis dot structure. Its Lewis dot structure looks like this. So 360 degrees divided up into three chunks. $120.
but so is that an incomplete dot structure?
We'll talk about why this one doesn't have a full valence, but basically boron is weird. It's not strong enough to pull electrons away from fluorine. Fluorine is too good at holding the electrons to itself. It won't share. So boron is like the baby brother with triplets that are all 10 years older. They'll share the bare minimum and then no more. All right, what about if we have four things? There's a better drawing. What's the furthest apart we could get four things around a central atom? 45? 360 over 4 is 90, right? you're headed the right way, but I had it wrong. Except we actually have more than 360 degrees to work with. Because these are three-dimensional objects. So if we actually arranged it so that it was flat, we use CH4. We're drawing on a two-dimensional surface. Yeah, the furthest apart we can get them is 90 degrees. But we actually have, if we just treated it like that, we're ignoring that there's this 180 degrees coming out of the board and 180 degrees going into the board that we could use as well. We can actually get them a little bit further apart if we use 3 dimensions. And we get something that looks like this. Right, so this idea, and then we'll take our break, is called valence shell electron pair repulsion, which is a mouthful, but it describes what's happening. The valence shell electrons are in pairs and they push away other pairs. So the acronym is VSEPR. Every class I've ever taken just pronounces it VSEPR, even though that's the wrong order of letters. It's close enough. So we'll call it VSEPR geometries. Just because VSEPR doesn't roll off the tongue so well. All right. So we're going to do some practice with these after break. Let's come back at 11:25. And we'll get more practice with Lewis-Dot structures, and then we'll start looking at what these molecules look like. If you haven't gotten your quiz back yet, come on up here. You'll probably have to remind me your name. Yeah. Gio, I have your quiz right here. R, right? Yeah.
If you want to, yeah, that's great. So that's
Yeah, there's.
doesn't.
I almost guessed, Carmen, but I didn't want to guess wrong.
Yeah.
All right, thank you, Carmen. I'm close. There's just a lot of you in this class. Yeah, sorry. So the easiest way to do it without writing out the configurations, you just start. So we're talking about nitrogen. Nitrogen is the second row. So we come over here to the beginning of the second row. 2, skip the D block, 3, 4, 5. That's it. Right, those are the white ones. Remind me your name.
Yeah. Literally. Oh. There's no weird practice, you know, like, ascending, like, it's 10.
Is it the same name for past the second?
Yeah.
Yeah, it is, but
Except that you don't count D block. So even though it's in the D block, those don't count as valence electrons. So everything in the D block just has a 2. Yeah. Because these ones go to that N equals 4 energy level, but then remember how the D orbitals were offset by a rho? So this is actually part of 3D. That means it's not part of energy level. So it doesn't count as valence electrons. So we're always going to skip the D block when we're counting valence electrons.
I guess it's that language.
No problem.
Or I thought the inventors. Okay, guys, yeah, we got the next one. So I'm very I think I need to go, especially after. Oh. I'm getting, I just get to, it was, with the, I can look at those slides showing what I'm gonna go. And so if it's repeat slides, I'm gonna go back to my slides. No, I had it in my slides, I'm like. It was really good. Yes. I thought it was just a single exact whenever. I was on this. No. Okay, covalent, polyatomic, atomic. Okay. So the covalent, right? Covalent, I think, share. Yeah, they share, right? Okay. So you use the prefixes, so like one is mono, two is di, three is tri, right? We only use those when it comes to the covalent bond. So then when it's C, hydrogen doesn't have nothing with it, so simply one word, we never use mono.
Yeah, okay, I understand like hurricane.
Okay.
When I tried this, like, I'm.
Okay, see then you gotta coordinate your periodic acids, because we're gonna go, no, I do. You guys meet tomorrow.
Yeah. She didn't tell me she wasn't coming.
Was she there this morning? I didn't see her.
Okay.
I really fucking hope not.
That was part of the mental performance. I really like it. I do think that was part of the mental performance today. I think he usually, well, I mean, last year, every time, the last 15 minutes of session was very slow. It was during all of it, we get more rest. They were good. I think it's because we're both now, he's just putting us on their program and we'll. I think in my, that's the guys I think, I know she's very. I called Greg out on his I saw him because he came into athletics. I was like, what are you doing here? You come on, oh, what? Oh, he doesn't go. Yes, you are. No, I told my manager, she's like, you need to tell them they have to. On this still.
Okay.
I work Saturday, so you can come in then. I'll text you. But yeah, he like came in because he does jujitsu there. I go, dude, like, how's the voice? Crazy. He's like, I'm sorry, you have Ryan. I'm backing. I mean, like, I like doing that exercise, but it's just like really. Yeah. It's okay. I love it better than this once. I love it. I love it so bad.
That was my ass off. I probably did.
Why never? You're touching my toe, and I was like, you're just like, I was like, this was you. She's in the only thing I could think of was killing me. It was like a little feather. The only thing I could think about is how literally my body is tingling. I cannot feel anything. And then, like, I don't know, the second group literally. They didn't do it. Yes, they did. They did. It feels longer when you're in there. Cause when I do my 3, 3, 2, 2, 1, 1, it's always longer. 3 minutes are longer than both of them. Yeah, but then the shoulders thing too. I never put my hands in, and so my hands like. I always I'll sit to like here, and that's it. I won't. I love the corner. Like my neck down, I was literally like sitting there.
My arms go in. See, like you. I didn't mean to touch my toes.
No, I know. I was like trying to sort of stop and shit.
I was literally like.
Okay, I have to. You get a good look. You get a good look. No. What Miranda said, it's Willie. What? Because it's really cute flower. It's really cute though. And it was really simple. So it's like. Okay, so this is my dream. Okay, and I was down at, I was like, that asked her to do like stripes on it. That would be cute. Where do you go? I already put. That's my mom's friend. Oh, just for free, so. No, I thought they were hearts. That's what I thought. Okay. Yeah, they looked red when you were pulling out. Literally, I didn't call it. No, no, that's all I'm gonna see. Stop. Like, there's a little bit of other things. No. Okay, it is for today. What did I do? I feel bad, like, I know it's always just in the dazzling, but I actually can't go, yeah. I almost picked some up out of the water too. I
You can't go?
No, she can't get off.
Does that mean Dre will be in it? The bowl.
So it's like, I was totally cool with moving it to Thursday, but nobody really tried. I mean, Zoe couldn't do it Thursday, we can do it, she work.
Yeah, on Friday we just.
Friday, I know you guys all have to go home, so that's what I suggested Wednesday. I would have said. Feel bad, it's like a 3-day weekend, I don't wanna like shorten things. Must have said, oh, Jay went home, me, well, she has an appointment.
She's going back.
I don't know, Monday.
Saying, but
That
that's
was
be
last
last
year.
year schedule. I'm going to see Thursday. Yeah. So that was my really. I'm looking for Mark that I.
I don't know, my cousin was.
Where are you guys this year?
I know, that's the first time I've been out since New Year's.
Did you guys get your stuff?
Yeah, I got rain. Oh, yeah, you had some.
That was some same website that I did. I did through the work with.
This is probably stuff.
Yeah, instead of paying $40 less. Sorry.
Just.
All right, let's start talking about what this looks like. Because this is that thing I was talking about the other day about thinking in 3 dimensions. Takes a little bit of practice because we're used to seeing drawings in 2 dimensions. So trying to visualize them in 3 dimensions is tricky. Alright, so there are a total of 5 shapes that that are fairly common. There's a 5th version that's a little bit less common that we're gonna leave off for now. But basically, the simplest ones you can kind of think about in 2 dimensions, or even in 1 dimension in the case of linear. If you're 2 electron domains, we're gonna use the term electron domains rather than electron pairs. Because an electron domain can be more than just 1 pair of electrons. It just means that there's one sort of area where you're finding these electrons. Right, so if you have 2 electron domains, they're naturally going to arrange themselves so that they're 180 degrees apart. If you have 3 electron domains, you get 120 degrees apart. Then it starts getting tricky because it's in 3 dimensions. So if they're 120 degrees apart, we call that a trigonal planar. Tri means 3, planar means flat. So if it's 3 electron groups, it's going to be flat and they're going to be 120 degrees from each other. We call that trigonal planar. If there are 4 electron domains, then we get this shape, like this rotating figure here. It's a tetrahedral shape. Anybody play board games that use some funky dice? Tetrahedral shape is a D4. The 4-sided die. Or you can also think of it as being like a 3-sided pyramid. The central atom goes to the middle. The points are the other ends of the atoms. for the most part, that's where we're gonna stop for this class. Right, because most of the things we're going to work on in this class are gonna top out at 8 electrons. And if they're all in pairs, that means you can have at most 4 electron domains. So nothing from the second row of the periodic table will ever be more complicated than a tetrahedral shape. When we get into the third energy level though, when we start getting d orbitals involved, we can have more than 8 valence electrons. And if we have more than 8 valence electrons, you can start getting more complicated shapes. And they're not actually that much more complicated. They look more complicated, but they're really they're basically just a combination of the shapes above them. If you have 5 electron domains, it makes a shape called a trigonal bipyramidal. So, but that's really just a trigonal planar with one thing sticking out and one thing sticking in. Right, if you look at it, it's 120 degrees, this what they call these equatorial position. These are also 120 degrees from each other, so it's trigonal planar, but then you also get the one sticking up and the one sticking down. So it's like a linear geometry stuck on top of a trigonal planar geometry. Basically, when we're limited to only 3 dimensions that we're working in, there's only so many ways you can arrange things before you start getting combinations of the things you already did. Then this last one is basically an octahedral geometry. If we have 6 electron domains, it's basically 3 linear geometries on top of each other. If you think about a 3-dimensional graph with an x-axis, a y-axis, and a z-axis, it basically looks like the x, y, and z-axis. You've got x, y, and z. And so everything is 90 degrees from everything else. And that's one of the reasons why we don't typically see anything beyond this. Is basically similar to quadruple bonds, we start running out of space. There's only so many ways you can put atoms around a central atom before it starts falling apart. Under really rare circumstances, you can actually make a pentagon bipyramid. If you think about having 5 things around the central instead of 3, 4, if you think about making 5 things around this central atom, and then one thing sticking up and one thing sticking down, that can happen, but it's really rare. And for this class, like I said, most everything is gonna stop here, this top row. So on the test, how are you supposed to show me that you understand what these shapes look like? This isn't an art class. So we basically have, so there's a couple ways to do it. You can either memorize the names, if that's easier for you. If the idea of drawing things is intimidating to you and you'd rather memorize their structures and what they're called, you can just tell me their name. You can say it's tetrahedral. If you can't come up with the word tetrahedral, you can draw it. Even if you're no good at drawing. I'm no good at drawing yet. But I can still draw something that's a tetrahedral geometry because we have these sort of shortcuts. And that's what I showed you the other day, but I'll put them up there again. If I want to draw a tetrahedral shape, I'm going to start with my central atom. And you put 2 bonds that are flat in the plane of the board, roughly 109 degrees from each other. Very few people can estimate 109 degrees with any sort of accuracy. So just make it about 120, make it a third of the way around, roughly. That's close enough. And then the other third, the other 120 degrees down into the right, is going to have one atom going into the board and one atom coming out of the board, sort of on top of each other. So the bond coming out of the board, we draw with a wedge, like this. And if you have the time and inclination, you can color it in. And that kind of looks like you took something that a stick and pointed it towards you. It's getting bigger on the side that's pointing towards you, is the thinking there. The atom that's going into the board away from us is basically on top of this one, but the opposite direction. So I guess it's behind this one. And we do that with dots. And if you take the time and go slow, you can make them get smaller as you're going, but the fact that it's dotted tells you it's going into the board. It's behind the board or behind your paper. So even though I'm no good at drawing, I can still show the three-dimensional shape as long as we all understand a wedge means it's sticking out towards you and dashes means it's going away from you. All right, and so that's our shorthand way for non-artists for showing three-dimensional perspective. Because you're not always going to necessarily have the computer with you. But now computers are so prevalent these days, you actually can pull up these 3D structures on your phone. There's programs that'll show you. There's web pages basically that are, and apps that'll let you build a molecule in 2 dimensions, and then you hit 2D to 3D and it'll show you the molecule in 3D, and then you can drag it around. In fact, that's what next week's lab is. Next week's lab, we're not meeting for lab because we don't have school on Monday, is going to be practice drawing shapes like this on a computer. And then you translate that into on paper, and that's what you'll actually turn in. But it basically says, draw an atom with a bunch of electron domains around it. What shape is it? Draw that shape. What's it named? And you're just going to go through that and work through, and you're going to wind up making a table that looks like this. And so this first column, these are the shapes we already talked about. Linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, or octahedral. Octahedral, be careful, because octahedral makes it sound like it has 8 electron groups. It's only 6 electron groups, but the way that you can arrange them far enough away from each other makes an 8-sided shape. So it's an octahedral shape, even though there's only 6 electron groups. Right, and in going along with the whole funky dice, that's an 8-sided die. You picture an 8-sided die, it looks like a 4-sided pyramid on top of another 4-sided pyramid. That's what an octahedral shape looks like. And so this table actually has the convention with the dots and the wedges. So this is looks a lot like what you're gonna draw for your lab next week. You're just going to do it by hand and and do your best and get some practice drawing these things. These sections over here, they're all derived from these electron geometries. So this first column, where everything that's attached to your central atom is identical, we call those the electron geometries. Because those are like the core shapes that everything else is built upon. The trick, though, is that we can't necessarily see lone pairs. Those non-bonding electrons that we draw in our Lewis dot structure, they still take up space because they're still electrons. They're still going to push away other electrons. But we can't see them. The only way we have of seeing these atoms, when I say seeing, I don't mean with our eyes. We can measure where the mass is in these atoms by doing things like shining X-rays on it. If you make a crystal out of a molecule and you shine X-rays on it, most of the X-rays go right through, like that gold foil experiment. But some of the X-rays hit a nucleus and bounce off at an angle. We can actually work backwards, do some trigonometry in 3 dimensions to figure out, based on the angle that X-ray comes off, where a nucleus is. So we can measure where a nucleus is, we can't measure where electrons are. So basically, if there's a lone pair, it still takes up space, but we can't see it. The analogy I use to help you wrap your head around that is, it's like somebody who gets on a school bus and then puts a backpack on the seat next to them. That backpack is still taking up space, nobody's gonna sit there. But if you're a driver at the front of the bus, you can't see why. You could guess nobody's sitting by that person because they put something on the seat next to them, but if you can't see what's on the seat, you can just see that there's empty space. That's basically what we're looking at with these electron lone pairs. Alright, so everything that's and so I don't like saying electron pairs. I'm gonna use the word domains. The number of electron domains is how many things are taking up space. If some of them are non-bonding electron pairs, they're still taking up space. So this, you still might have a trigonal planar overall shape. The electron geometry might be trigonal planar, but if you can't see one of the three pieces, it actually looks what we call bent. So we might see something that looks like, I think, SO2 is an example. If you draw the Lewis dot structure for SO2, you get something that looks like, actually we'll draw it. I'm not going to draw the Lewis dot structure showing you things that I haven't taught you yet. This isn't the best possible Lewis dot structure, but is a Lewis dot structure for this molecule. You've got three things taking up space around the sulfur. It's electron geometry. Is trigonal planar. Because the electron geometry is just, what is the shape if we could see where the lone pairs are? And so your electron geometry is always going to be that first, something out of that first column on that table we just had up. The molecular geometry says, okay, but now you remember you can't see the electrons. And if we can't see the electrons, they're still there, they're still taking up space. This doesn't automatically become linear just because we can't see the electrons. That backpack is still on the seat. So it stays in the same shape, but we can't see the third electron domain. And so we call this the molecular geometry. Is based on the electron geometry, but you can't see something. The name of this geometry is bent. All right, so we're going to be very specific about what type of geometry we're talking about. Electron geometry is always from this first column. If it has no lone pairs, its electron geometry is the same as its molecular geometry because you can see everything. If there's a lone pair though, based on how many lone pairs you have, you stay in the same row as your electron geometry and you look over. Right, so NH3, ammonia. Lewis dot structure for NH3 looks like this. How many total electron domains do we have? 4. So it's electron geometry is tetrahedral. But because we can't see one of those when we erase it, the molecular geometry doesn't look tetrahedral anymore. So if I draw this in showing the perspective, So it looks tetrahedral, right? One thing flat in the board, another one flat in the board, one into the board, one out of the board. Everything's 109-ish degrees from each other. But then if I say, okay, my molecular geometry, I can't see that lone pair. The hydrogens still stay in the same spot, just because they don't move just because I erase the lone pair. The lone pair is still there, we can't see it though. I'm overemphasizing that point because what I see over and over again on tests is that people will do this and then they'll say, okay, the molecular geometry is trigonal planar, because there's three things I can see. No, because everything still stays in that same shape. We just can't see one of the four objects. So the molecular geometry for this one is going to be trigonal pyramid or pyramidal. A three-sided pyramid, basically. Right, so now we're getting into why you might want to draw these on the test instead of memorize these names. Memorizing these 5 names, that's not so hard. There's only 5 of them, their names are pretty descriptive of what they are. Rest of these can get really painful to memorize. If you would rather draw them, that's a full credit answer on the test. The test will say, here's a molecule, draw the Lewis dot structure, that's 3 points. What's the molecular geometry? That's 2 points. What's the polarity? That's 2 points. We'll talk about polarity in a second. So you can memorize these names or you can draw them, but you have to be able to draw them somewhat close to the right angles. You have to use the wedges and dashes where appropriate. Easy enough, right? It's just one slide. How complicated can it be? Well, there's the whole fact that to do this, you need to do the Lewis dot structure. And to do the Lewis dot structure, you have to be able to count valence electrons. To count valence electrons, you have to know how the periodic table works. So this class builds on itself. Even though this is just one slide, albeit a complicated slide, you have to be able to do the rest of this stuff too in order to get it right. So with that in mind though, to reassure everyone, if you make a mistake in your Lewis dot structure, that's obviously going to throw off your answer for your molecular geometry, right? I won't mark you down twice. So be consistent with your own answer. Even if you get the wrong Lewis dot structure, try to do the molecular geometry so that it's consistent with what you drew. Right? If you are consistent with what you already did, I'll only mark you down once. And so when I'm grading, you'll sometimes see there's two abbreviations that I use for this. Wrong but consistent means that it's not the right answer, but it matches what you did earlier. If it's wrong but consistent, I'm not going to mark you down more points. The other option is right but inconsistent. That's a bigger problem. If you get the right answer, but you got the wrong Lewis dot structure, not only am I going to mark you down for that, you're going to get marked down twice, once for getting the wrong Lewis dot structure and once for being inconsistent with your own answer. That also makes me look at your stuff a lot more closely to see if you're actually cheating somewhere. Because how could you get the right answer if you were wrong the step before? Maybe you just guessed right. Maybe you had offsetting errors, but I start looking more closely when I see that. Right but inconsistent is not where you want to be. Better to be wrong but consistent with what you already did. Does that make sense? So, maybe I counted my valence electrons wrong. So if I was looking at NH3, like we already did, maybe I counted the electrons on the nitrogen wrong, and I only got that I had 5 valence electrons to work with instead of 8 valence electrons to work with. So I might draw a Lewis dot structure that looks like this without the lone pair on top. If I was going to say what's the electron geometry for that, that looks like there's 3 electron domains, right? Based on my Lewis dot structure, so I'd say trigonal planar. If I draw this for my Lewis dot structure, but then I say it's tetrahedral electron geometry, that would be right, but inconsistent with what I drew. Don't do that. Be consistent with what you already did. Right? And trust me on the partial credit. Not to harp on the cheating thing, but I'm still dealing with headaches in some of my other classes where I'm still dealing with academic dishonesty, hearings and things like that. So don't do that. It's not worth it. And if you copy down something that you don't understand, you run the risk of being right but inconsistent, which makes me look harder at it. Don't turn in things you don't understand. All right, this is just a better drawing of what we have here. This is the way that we would draw them with the wedges and dashes. If you actually have a computer rendering these for you to make it look better, this is the same thing. If it's tetrahedral versus trigonal pyramidal, it's still tetrahedral, we just can't see that lone pair there. And bent is still tetrahedral, it's just got 2 lone pairs that we can't see. SO2 is the same. Right, it's got 1 lone pair we can't see. So, questions on these geometries? It all comes back to the Lewis dot structure. So we're going to get good at doing Lewis dot structures because that's going to help us with these. But there's one more topic I want to cover today so that we're set up for that lab next week. And that's the idea of polarity and electronegativity. So electronegativity is one of those periodic trends where the shape of the periodic table tells you something about it. So we already talked about those for like atomic radius or ionization energy. Electronegativity is tied to ionization energy. Basically, the harder it is to take an electron away from something, the more it's going to pull electrons towards itself. So electronegativity is basically who's strongest when we're making a covalent bond. Electronegativity is how much does it pull electrons towards itself. Right, and so we basically have these arbitrary numbers. There are units to electronegativity, but we never do any calculations with them really. So the units don't really make sense. They're called degrees Pauling, after Linus Pauling, who was the person who invented this scale. And so basically the way we determine whether or not you have a polar bond, a polar covalent bond, it just means that you still have a covalent bond. Electrons are being shared between 2 atoms, but they're not being shared evenly. Whatever's more electronegative is better at pulling electrons towards itself. So the analogy I always use is it's like sharing a bed with a blanket hog. Right? If you've ever stayed in a hotel with your siblings or significant other and wake up in the middle of the night and they have all the covers and you have no covers, they're more electronegative than you are. They're pulling the electrons towards themselves at your expense. And just like with your significant other or your siblings, it's not entirely intentional. Maybe not intentional at all. I don't know. With my oldest definitely intentionally steals the covers in the middle of the night from my middle. But it's just a function of the fact that fluorine really wants to gain electrons and pull electrons towards itself. It has more protons in its nucleus than the oxygen does next to it, right? So it pulls electrons in tighter. If you force fluorine to share electrons with nitrogen, the fluorine, they still are in both valences at the same time, but they're more in fluorine's valence than they are in nitrogen's. Right, and so what that looks like is this figure down here. If we have a non-polar covalent bond, so we have two equal atoms on either side of this bond, they're going to share the electrons evenly. But if you've got one blanket hog and one non-blanket hog, the electrons migrate one way basically. They're more towards one side of the molecule than the other, one side of the bond than the other. And the way we say that is with these partial charges. It's not a full charge because we don't actually have electrons changing hands. It's still a covalent bond, but it's not being shared evenly. And so the symbol we use for that is this little lowercase delta. So this means a partial positive versus a partial negative. It just means that there's more electrons on this side than that side. They're not being shared evenly. Then if you have a large enough difference in electronegativity, then it's not a covalent bond at all anymore. Once you get above a certain threshold, you actually get an ionic bond. And so that's sort of what dictates our difference between our metals and our nonmetals on the periodic table, is the more electronegative something is, the more of a non-metal it is. The better it is at pulling electrons towards itself. So if you put a metal with a non-metal, there's such a big difference in electronegativity, it doesn't share electrons at all. You actually just get electrons changing hands. Your non-metal gets to keep the electrons. Right, and so there's this somewhat arbitrary scale. It's a spectrum, but we have sort of an arbitrary cutoff. Where we say, okay, if the difference in electronegativity between the two atoms is 0.4 or less, we call that a nonpolar bond. And if it's between 0.4 and 1.8, it's a covalent bond, but it's polar. And if it's a larger, and this is, don't get hung up too much on these numbers entirely because some textbooks say 1.8, some say 2.0. We're not going to get too bogged down in that. Either way, once you get above a certain point, it's actually an ionic bond. It's not a covalent bond at all anymore. All right, so let's do a practice problem. This molecule, CH2Cl2. Let's start with its Lewis dot structure. And we'll talk about its VSEPR geometry for practice. And then we'll talk about which bonds are polar. So I'll give you a head start. Start with the Lewis dot structure. What's your name? Right? Communicate. talk. It's fine. Quiet questions make me nervous. Oh, it's an easy fix then. Does that matter? What's the shape of the molecule going to be?
1, 2, 3, 4, 5.
Oh, Lewis dot structure. Always start with that. Can't answer questions about polarity unless we know where the bonds are. Count up your electrons. I get 20 valence electrons. Carbon's got the most vacancies. And here's the other kicker. If you have multiple atoms that have the same number of vacancies, whatever is less electronegative goes in the middle. Because you're forcing it to share more if it's in the middle. So you're never going to put the most electronegative element in the middle. I said never. I shouldn't have said never. There are rare cases. For the most part, whatever's got the most vacancies will also have the lowest electronegativity. Kind of. Right? Because hydrogen's less electronegative than carbon. But can hydrogen go in the middle? Because it can only make one bond, right? You can never put a hydrogen in the middle because how do you put something in the middle that can only make one bond? So with some caveats, whatever's least electronegative is going to go in the middle. We draw 4 bonds. Carbon to hydrogen, carbon to hydrogen, carbon chlorine, carbon chlorine. That used 8 electrons. Carbon's now got a full valence already. Hydrogens are satisfied. We have 12 electrons left. Each of the chlorines still needed another 6. 2 times 6 is 12. So when we divvy up all of our electrons and satisfy the chlorines, we've used 20 electrons total. And everything has a full valence. So we're good. What's the shape of this molecule going to be? What's the VSEPR geometry of that carbon in the middle? How many electron domains around the carbon? 4. 4 electron domains, tetrahedral. Are any of them lone pairs? None of the electrons or electron domains around the carbon are lone pairs. So we know that its molecular geometry is the same as its electron geometry. It's just straight tetrahedral. Do these count as electron domains? Say that louder, Corbin.
I said for the chlorine, they do.
So the chlorine is going to have its own VSEPR geometry. Every atom has its own VSEPR geometry. We say molecular geometry, but that's a bit of a misnomer. Because as we start building larger and larger molecules, we'll start seeing that every atom has its own shape. And when you put all of them together, you get an overall shape of the molecule. So that's exactly right, that the chlorine has 4 electron domains. So it also has a tetrahedral electron geometry. This carbon has its own geometry that's separate from the things around it. It's based on how many things around it. But don't count these electrons as part of the electron domain. these electron pairs count for the chlorine, not for the carbon. All right, last step here. Which bonds are polar? What's the difference in electronegativity between carbon and hydrogen? So carbon's 2.5, hydrogen's 2.1, so 0.4. It's like right at our threshold. Basically, this is sort of what we use as our dividing line. If it's a bigger difference than carbon to hydrogen, it's polar. Carbon to hydrogen is non-polar. Right, so I don't bother remembering the 0.4 number. I just know I'm going to compare everything to carbon and hydrogen because molecules that are just carbons and hydrogens are sort of our definition of non-polar in the chemistry world. They're called hydrocarbons, like gasoline, oil, things like that. They don't mix with water. They're completely non-polar. So we use carbon to hydrogen as our threshold. Anything that's a bigger difference is polar. So with that in mind, these are non-polar. What about carbon to chlorine? 0.5, so that's above that difference that we just said, right? That's above that 0.4 threshold. So carbon to chlorine is a polar bond. I don't know why it's so hard to take notes. This is totally legible, easy to read, right? All right, here's the other way that you can remember. So I'm going to give you a chart that looks just like this on your test. It'll be right above the periodic table. You're going to have these numbers so you can go back and check. The other way that you can remember it, if you don't have these numbers sitting right in front of you, is that there's sort of a Mount Rushmore of electronegativity. Nitrogen, oxygen, fluorine, and chlorine are more electronegative than anything else. But basically, there are some caveats, but for the most part, if you see anything attached to one of these four, it's going to be a polar bond. Like I said, there's a little bit of wiggle room, but those are the ones to always look for. So when you get used to that, you don't even need to look at those because you can say, oh, I've got carbon chlorine bonds, that's polar. Boom, I know that because chlorine is involved. Why does this matter though? Why do we care? Because like I mentioned, I just used an example of hydrocarbons don't dissolve in water. Oil and gas don't dissolve in water, they sit on top of water, right? Polarity of a molecule determines some of its macroscopic properties, like what's its boiling point, what's its melting point, will it dissolve in water? Can you dissolve in other things in it? Anybody who's ever tried to clean a bacon pan, a pan used to cook bacon, knows that polarity matters because you can't just use water to clean bacon grease, right? You try to use water to clean bacon grease, you're just spreading grease around. You need to use other molecules that have similar properties to the bacon grease in order to clean it up. And same with if you've ever worked on a car, gotten grease on your hands or something like that before. Water alone doesn't cut it. You need soap. You need acetone, or you need something else that allow you to dissolve those molecules. And that's all based on the polarity. Water is a polar molecule. It won't dissolve non-polar molecules. Right, so we've talked about polar bonds. to determine if a molecule is polar, we add one more layer to it. Because that's what we do. I teach you something, we practice it a little bit till you get halfway comfortable, and then I add another layer to it. For a molecule to be polar, it's gotta have polar bonds. Easy enough, we just learned how to do that. Lewis dot structures are a pain, but we can do it. We're getting better at it. The molecule also has to be asymmetric. And that's where the VSEPR geometries come in. Because if the molecule is not asymmetric, even if you have polar bonds, they're pulling in exactly opposite directions. So to go with our sharing a bed with a blanket hog analogy. Our 3-year-old climbs into bed in the mornings on Saturdays and lays in between me and my wife. We're both blanket hogs. We're constantly pulling back and forth between each other. That works out fine as long as there's only the two of us in the bed, right? Because we're balancing each other out. So it's like two really electronegative elements forming a bond, like say fluorine forming a bond with another fluorine. Even though both of them are blanket hogs, they're equally strong and pulling in opposite directions. So the electrons are still shared evenly. If you take a less electronegative element, a 3-year-old, and put it in between two blanket hogs, that still doesn't change where the electrons are, right? The blankets are still on top of him. They're not being pulled either way because you have two equally strong atoms on either side. That's why you have to have asymmetry. You need to have a net pull one way versus the other in order to have a polar molecule. So if I'm stealing the covers from my 3-year-old, that's easy enough. If I'm trying to steal the covers from my wife, we're balanced out. It doesn't matter that the 3-year-old's in the middle because he's not really affecting. The other analogy you can use is tug of war. Oxygen's is like an NFL team playing tug of war. Carbon's like a high school football team playing tug of war with an NFL team. It doesn't even matter that the high school team's there, right? Really, it's the two NFL teams playing tug of war with each other. And the carbon's just along for the ride. All right, so how do we determine if we have asymmetry? You look at the geometry. Basically, you look at how many electron domains you have around that central atom. And as long as one of your electron domains is different than the others, then you have asymmetry. So, going back to this molecule. Does it have asymmetry? Let me redraw it. Show it in tetrahedral shape. Is it symmetric? Is there a net pull one way versus the other? What's pulling the electrons in this molecule? What's the biggest bully? So carbon is more electronegative than hydrogen. So carbon's pulling electrons from the hydrogen, but chlorine is more electronegative than the carbon. So the chlorines are the most electronegative thing here. They're pulling the electrons towards themselves. Is one part of this molecule going to have more electrons than the other side? Yeah. This area by the chlorines is going to have a partial negative because the chlorines are more electronegative than the carbon. This side of the molecule is going to be a partial positive because the hydrogens are less electronegative than the carbons, which is less electronegative than the chlorine. So this molecule as a whole is polar because one, it has polar bonds. And 2, it has asymmetry. What if I replaced these hydrogens with more chlorines? It still has polar bonds, right? Carbon to chlorine we already established is a polar bond. But now it's symmetric. Now our electronegative elements are equal in all directions. If it's perfectly symmetric, if all 4 things around the carbon are the same, we can't have an overall partial negative anywhere because it's our NFL teams playing tug of war with each other. They're not really going to make much headway because they're all equally strong. And so this is not a polar molecule. As soon as one of these is changed to something else, it's polar. So, in fact, we just make it, change one of those to a hydrogen. Now, all 3 of these chlorines are still kind of fighting with each other, but there's still an overall partial negative on the top right corner of this molecule, right? And this is another molecule you've heard of. They used to use it all the time in like police crime dramas and CSI and things like that. This is chloroform. Chloroform is like what they put the rag on and then like magically you immediately fall asleep anytime it gets anywhere near your face. They did that a lot in the early 2000s. Chloroform was like this magic bullet that automatically knocked somebody unconscious and they would wake up several hours later feeling fine. Turns out that's not how chloroform works. It will knock you out, but you are going to wake up pretty quickly and with a nasty headache. Unless they keep the rag on your face, in which case you're just more likely to die. So, not the best molecule for actually doing any of that stuff and kidnapping people or whatever. Don't put chloroform near someone's face. This is the bullet point here. You leave this lecture with one thing. Don't try to knock people out with chloroform. All right. So here's some more practice, including formaldehyde that we drew earlier. We already have the Lewis dot structure drawn for that one, but you can redraw it for practice. We're going to end lecture here today. We come back next Wednesday, so I'm not going to see you for a week. So, practice your polyatomic ions. If you haven't had lab yet this week, we'll talk about polyatomic ions in lab today. And we will not have a quiz this weekend. Do that lab assignment, the Vesper geometry assignment that has, I think, a few questions about polarity, so you get to practice this a little bit. And I'll see y'all in a week. All right, have a good day.